Welcome back to my sunroom where we are still discussing nuclear chemistry. Right now we're going to focus on half-life. So what is half-life? Hopefully you've already read from chapter 25 in the packet that I handed out. We are on page 804. Hopefully you read that half-life is simply the amount of time that it takes for a substance to decay to be half of what it used to. So this is how long, if I have 1 gram of carbon-14, how long does it take to have half of a gram of carbon-14? That's all half-life means. We use it for a lot of things, but half-life itself is very simple. You can think of it as in terms of soda losing carbonation. So you know that if you leave a cup of soda sitting out, that it's going to lose carbonation. If you start with a brand new fresh can of soda and you pop the top, you can assume right there that you have 100% carbonation. The amount of time that that takes to get to 50% carbonation, so not completely flat, but not fresh, crisp, and refreshing, that would be a half-life for the carbonation of soda. When we talk about half-life, in terms of radiation, we're talking about how long it takes for a particular element to decay, usually through alpha decay, like we talked about in the last video. The most famous example of this is carbon-14 that's used in carbon-14 dating. Your book presents carbon-14 dating as a more sure science than it is. I would highly recommend that you guys take some time to look up maybe some of the limitations to carbon-14 dating. Or maybe it'll be another video for me. For now, let's talk about half-life. So when you are given a half-life problem, you can flip to page 806 to follow along with an example. In a half-life problem, you are going to be given a few pieces of information. For instance, in the sample problem 25.1, it reads carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume that you start with a mass of 2.0 times 10 to the negative 12 grams of carbon-14. How long is 3 half-lives? How many grams of the isotope remain at the end of 3 half-lives? Let's look at this together. We are starting with carbon-14. Make sure that you guys can see that. Carbon-14 means that you have an atomic weight of 14 while you still have 6 protons, because carbon always has 6 protons. Normally, carbon is a 12 and a 6 because it has 6 protons and 6 neutrons. However, in carbon-14, you have 8 neutrons, 6 protons. For the half-life, which we write lowercase t subscript half, is equal to 5,730 years. Essentially, this stuff is not going anywhere quickly. So what they want to know is how long does it take to reach 3 half-lives? This is so simple, guys. 3 times 5,730 years. All right? It's like asking, how long does it take for you to have 3 birthdays? Well, 3 times a year. That's how much time it takes you to have 3 birthdays. That's essentially what they're asking. How long does it take for this to happen 3 times? Well, 3 times whatever time it takes. Doesn't matter what the half-life is. For this particular one, 3 times 5,730 is 17,000 years, 17,190 years. Again, not quick. Next, they want to know how many grams of the isotope will remain at the end of 3 half-lives. Let's not get hung up on vocabulary. Isotope is just the big fancy chemistry way of saying the other form of carbon. So how long does it take carbon-14 to be cut in half 3 times? in order to do that, you've got to know the original mass. The starting mass that they gave us was 2.0 times 10 to the negative 12 grams. This is the starting mass. You guys see that? Starting mass. I'm going to multiply that times 1/2, and then we're going to set an exponent for the number of times that the half-life has occurred. So if we were just trying to figure out one half-life, we would do an exponent of 1. In this case, they told us the half-life has occurred 3 times. Okay? So I have the starting mass. I have 1/2 because we're talking about half-life. And then I have an exponent that is the number of half-lives. When I plug all of this into my calculator, I come up with an answer that is 0.250 times 10 to the negative 12 grams. It's essentially like multiplying 2.0 by 1/8. All right? That's the answer we're looking for. So that is how you are going to find, that's how you use half-life in a problem. Let me erase this, and I'm going to do one more practice problem with you guys, also found on page 806. My poor whiteboard is old. Would probably be easier to see it if I used a baby wipe. All right, so the practice problem number 7 on the bottom of page 806 says manganese 56 is a beta emitter with a half-life of 2.6 hours. What is the mass of manganese 56 in a 1.0 milligram sample of the isotope at the end of 10.4 hours? Hopefully you're reading along with me because that was a lot to take in just hearing all those numbers. The first thing that we need to remember is how to figure out the number of half-lives at the total time for a sample. So I think we looked at one of these triangles when we did density, when we said density is equal to mass over volume. So here's an example problem. Density is equal to mass over volume. And we said we can fit this into this triangle, and then you can always figure out, if you just cover up the one you're looking for, it'll show you whether you're multiplying or dividing. Same kind of thing with half-life. To figure out that question that they were asking, which is, if the half-life is this time and it's been this many years, how many half-lives have happened? Okay? You put the total time, that goes at the top of your triangle. Total time. That's very hard to see. I need to write bigger. All right, let me do that. Here's where my cheap Expo marker gives out. So, total time. In the bottom two, you have the number of half-lives next to the actual given half-life, all right? You are going to be given t of 1/2. You will either be given it in the problem or you'll be able to find it on a table. This is not something that you ever have to memorize. The total time, that should also be a given. Or the number of half-lives that have passed will be a given. Either way, as long as you have two of these three things, you can figure out the third one. In this case, they have given us the total time, and they've given us how long the half-life takes. So if we fill in our triangle with the information that they have given us, we have 10.4 years, and they told us that the half-life of this sample of manganese is 2.6 hours. All right, 10.4 years, 2.6 hours. This is a division problem. When I divide 10.4 by 2.6, I find out that the number of half-lives is 4 half-lives. Right? Now I can answer the rest of the problem. Because the problem they asked is how much manganese 56 will be left from the 1.0 milligram sample at the end of 10.4 hours. Now I can plug 4 into the problem that we used a minute ago, where we start with the mass, which is 1.0 milligrams, and we multiply it times 1/2 with an exponent of 4. See, the 4 moved from here to here. This was given to us, 1.0 milligrams was given to us in the equation. We always multiply by half because we're talking about a half-life. And the exponent is the number of times that the half-life has happened. When I plug all those things into my handy-dandy calculator, I get 6.25 times 10 to the negative 2 milligrams. 6.25 times 10 to the negative 2 milligrams. These problems, as long as you can remember these two formulas, that you're doing the mass times 1/2 to an exponent of the number of half-lives that have passed. And if you can keep in mind this triangle where we have the total time, the number of half-lives, and the actual half-life, you have got your half-life problems. That's all there is to them. Let me know if you guys have questions. I'm sorry the bunny was really noisy, especially there at the background. Another video, I will see if Gandalf wants to join us.